started log functions, and every single section after this is going to be all about logs. So we have to remember a few things from Algebra 2. We're going to start with the definition, and the definition is really just changing its form. Do you guys remember what you can rewrite a log function as?
Exponential.
Yes, exponential. Do you guys need more time to write down your objective for today? All right, so definition of a log function is if you have log base b of x equal to y, you can write it as, and this is a double-sided arrow because it goes both ways, you can write it as b to the y power equals x. So the main thing I do like to point out is the base. Okay, the base of the log is the same thing as the base of your exponential function. Okay, it's a logarithmic function if it has log in it. It's exponential if it has an exponent. Okay, and an exponent that is a variable. One way you can remember this is bay if you're looking at the log function. So this is your base, this is your answer, this is your exponent, right? So this becomes your base, this becomes what it's equal to, the answer, and then y becomes your exponent. But again, that's if you're looking at it from the log. So you have to look at it from the log point of view. If you have numbers, it's a lot easier to put it in that form because it has to be true. So if you had 2 cubed was equal to 8, you'd know that that was right. If you had 2 to the 8th equals 3, well, no, 2 to the 8th does not equal 3. You could figure it out that way. If you're looking at a natural log function is just a log with a base of e. So log base e of x is written as natural log of x. Okay, that's called your natural log function. And then just like in this format, if you had the natural log of x was equal to y, you could rewrite this as e to the power of y equals x. Now, the relationship between logs and exponential functions is that they are, do you guys already know? Inverses. Okay, so exponential functions and logs with the same base are inverses. So exponential functions and logs with, and it has to be with the same base, are inverses. And inverses undo each other. Okay, so if they have the same base, you're going to notice that some things cancel out. We have these list of properties, first for just logs, and then for natural logs. The same thing's going to apply, but we're going to go through and write down why these make sense as our properties. So the first one says log base a of 1 equals 0. Is it okay if I zoom it in? Okay, so log base a of 1 equals 0. So we must raise a to the power of 0 to get 1. Let's just rewrite this as an exponential function. So if my log base is a, my base of my exponential function is a to the 0 equals 1. Well, yeah, isn't anything to the 0 power 1? Yeah, so this property is telling you if you take the log of 1, what are you going to get? 0, right? Isn't that what this is telling you? The log of 1 equals 0. Doesn't matter what your base is as long as it would fit in here. If I have log base a of a equals 1, well, yeah, a to the first power equals a. That makes sense, right? You can also think of this as when you had the log base a of a, those would cancel out and you'd be left with 1. with this one, again, if you're writing this in terms of an exponential function, you'd have a to the x equals a to the x. Well, yeah, we can see those are the same. You can also think of it as if you have log base a of a to the x, because the log base and the base are the same, those cancel out, you'd be left with x. Which, I mean, this is something that you definitely did in Algebra 2. We'll review that again today. With this, if you have a to the power of log base a of x, just like they canceled out here, they're going to cancel out. So even if the exponential function has the log in its exponent, it still cancels out. Doesn't just have to be the log first. And then for these, again, it's the exact same thing. The only difference is it's with the natural log. So the natural log of 1 is 0, right? The natural log of e equals 1. The natural log in e are what type of equations? Inverses. Okay? All right, so we're going to evaluate each expression. We're going to do this part without a calculator. You do not need it. And when you're evaluating the expression, there's really two main methods we want to focus on. The first is you want to rewrite whatever the log is of with the same base as the log. Okay, so I want you to do that for part A. So try to rewrite 36 with the same base that we have here. Okay, so Reese, how can I rewrite 36 with a base of 6? Oh yeah, yep, you can think of it like that, but how am I going to rewrite 36 with a base of 6? So 6 to what power would be 36? Yep. And then based on this property up here, right, log base 6 and 6 are going to undo each other, which means what would I be left with? Log base 6 and 6 cancel out, I'd be left with what? Be left with 2. What Reese said is actually the second method. So you can rewrite with the same base as a log, or okay, you can use the log definition to rewrite as exponential. Okay, so you could rewrite as an exponential equation. Now, this doesn't have it equals anything, but that doesn't matter. You can think of it as y equals log base 6 of 36. And then Reese was saying, oh yeah, 6 to the y equals 36. And 6 to what power would make 36? 2. Okay, so you can think of those either way. When you're rewriting this one, you have log base 10. 10 to a power is going to equal the square root of 10. How do I rewrite the square root of 10 as a power? CJ, do you remember? Yes. Okay, so if I had 10 to the power of 1/2, right, that means the square root, so these would undo each other. I'd be left with 1/2. You'd still have to know that if you did the second step, which would be 10 to what power equals the square root of 10. You'd still have to know that the 1/2 power is the square root. And it's nice to just put that little note there in case that's not something we remember until we're reminded. Right? Just like if it's the 1/3 power, it's the cube root. The 1/4 power, it's the 4th root. Okay, now for C, you can see that you have the base of 3 and the log base of 3. which according to our last property means those are going to undo one another. I'd be left with 8. Those ones are nice, huh? Okay, now for D, I have log base 8.25. So, if I'm looking at this, right, it's not that easy to convert 0.25 to a base of 8. So I might want to think of this one as 8 to some power, which we've been calling it y, equals 0.25. But still, I might want to think of 0.25 in terms of what? What's another way I can rewrite 0.25? A fraction, 1/4. Good. Now, is 8 to a certain power going to be 4? No. Well, I mean, technically, it will, but not a whole number, right? Like, you can't just take the square root of 8. You can't raise 8 to the second. It's a smaller number. So instead of trying to rewrite it with a base of 8, let's rewrite these with the same base. We're going to rewrite both of them. Okay, so rewrite both with the same base. Because when you look at 8, right, what do we know 8 can be rewritten as? Yeah, 2 to the third, right? So 2 to the third to the y power. Can I rewrite 1/4 as a power of 2? Mm-mm. Okay, so ask yourself 2 to what is going to be 4? 2 squared is 4, right? Okay, so if you want 1 over it, it has to be negative. Remember, if you have a negative, that's what puts the 1 over it. So this would be like 2 to the negative second, right? Because 2 squared is 4, so 2 to the negative 2 is going to be 1 over 4. So I have 2 to the 3y power equals 2 to the negative 2. What is something I know now from this setup? Like, why would I want them to be the same base? Okay, so if their bases are equal, what else has to be equal? Their exponents. If their bases are equal, exponents are equal. They have to be, right? I can't have 2 to the 5th equals 2 to the negative 2nd. Then would they be equal? No. Okay, so because the exponents are equal, I can use this and I can solve. So, okay, my exponent has to be negative 2/3. So let's think about what happened here. I need to go from 8 to 1/4. Because I was going to something that was a fraction, I used the negative. And because I was going to something that was smaller, I had to have a fraction in the first place. Now let's check this. So if I have 8 to the negative 2/3, if I evaluate this, I should get 1/4. Well, if I have a negative exponent, how do I undo the negative exponent?
1 over.
Yep, so 1 over 8 to the 2/3. All right, this is what we did in chapter 1. If you have a rational exponent, 2/3, how can you rewrite this?
8 squared. Or the cube root of 8 squared.
The cube root of 8 raised to the power of 2. Do you guys remember that rule? Maybe we should write that one down too. So our rule that we're using is a to the power of m over n equals the nth root of a to the m power, or the nth root of a to the m inside the radical. Do you guys remember that? I said if it, how do we remember it's a root, that the root is the bottom number?
Roots are below the ground.
That's right, roots grow in the ground, and the power is on top. Good. All right, that's my crown. So if I rewrite this, the cube root of 8 squared, well, what's the cube root of 8? 2, so 2 squared is 4, 1/4 is 0.25. Yep, we did it right. Okay, so this type of thing's going to come up again whenever you have your fractions. All right, now here I have natural log of 1 over e. So let's rewrite it with the same base. What's the base of the natural log? E. So I want to think of this as the natural log e. If it's 1 over e, what's the power? Negative 1. Right? E to the negative 1 is 1 over e. Natural log and e are going to undo one another, so I would just be left with negative 1. Okay, so start to think about the relationships between these. The log and the exponent, right? When you're taking a log, you're just trying to find the exponent of your exponential function here. All right, now the next thing says to use the definition of the log function to find x. And all of our equations here are logs. If we look at the log definition, that tells us if we have something that's written as a log, I can rewrite it as what type of function? Exponential. So when it says that you're using the definition, you're going to be rewriting as an exponential function. All right, so go ahead and write your equations for A, B, and C. Okay, so do that first and then go back and then solve them if you can. Okay, so make sure that you guys are showing that how you found it. So if you're using your definition, okay, I just gave you time to rewrite these as exponential functions, so that's what I want to see. Okay, so Anna, what was your exponential function for A? 2 to the 5th equals x. Good, 2 to the 5th equals x. And what is 2 to the 5th? Yep, good. All right, and then Emma, what about for B? What was your exponential?
3 to the x equals 240.
Good. And we'll do this one too. Logan, what's your exponential equation for this?
X to the 3 over 2 is 8.
Good. All right. Now, this one was pretty simple, right? 2 to the 5th, we got that. This, we're going to have to find 3 to what power is 243. I feel like we all should know 3 cubed off the top of our head, right? 3 cubed is 27. If you think of 3 to the 4th, 3 to the 4th is 2 pairs of what? If I have 4 3s, it's like I have 2 9s. So 9 times 9 is 81. So really the first thing I'm going to want to check is to the 5th power. To do the 5th, I just have to take 81 and multiply by 3. What's 80 times 3? 240. And then 3 times 1 is 3, so it'll be 243. Yep, so this would be x equals 5. Right, now, with some of you that were doing this, you probably, because I saw some of you guys had your x, but you didn't have any work with it, were you guys testing numbers that you could take the square root of and then raise it to the 3rd power? Well, Logan, how'd you get yours?
I'm gonna be honest, that way.
You take the cube root of both sides, you end up with
That's what I did?
x to the 1/2 is
Oh,
equal to
that's
2.
what I did then.
Okay, so you did the cube root of both sides
Yeah, take the cube root of both sides.
to
you
undo
end
the
up with-
power, and then you'd have the 1/2.
Yeah, x to
Okay.
the 1/2 is equal to 2.
All
Square
right.
both sides.
Okay. Let's think of another way we can do it. So if you just had 3/2 times x, right, not as an exponent, how would you move over 3/2 or any fraction? What do you do to move it over to the other side? Okay, you flip, which is called the reciprocal, multiply by the reciprocal, right? This is the same thing, except instead of multiplying by the reciprocal, we're going to raise it to the power of the reciprocal. So if I raise this to the power that is the reciprocal of 3/2, then 3/2 times 2/3 is just what? Which is 1, right? That's the whole reason why we multiply by the reciprocal in the first place, to get 1. So this would just be x. And then all I would have to do is evaluate 8 to the 2/3, which we just talked about, would be the cube root of 8 squared. The cube root of 8 is 2. 2 squared is going to be 4. Okay, and then that's why 4 is going to be your final answer. So again, if you have a power like this, then you can raise each side to the reciprocal. Okay, so you can always raise each side to the reciprocal in order to solve. All right, I'm going to give you a couple minutes. I want you to look at this graph and then start to answer these questions. And the first two are review. Okay, so Devira, what's one of the inverse functions? Okay, so y equals, just say a to the x. Yep, or to the x power. Okay, good. And then Corbin, what's our other one?
The log base A of x.
Yes, log base a of x. So how can you tell from the graph that these are inverses? What did you guys say? Or what do you guys think? What do you remember? Yeah, Joey.
The y's and the x values, like they swap.
Good. Okay, so there's two of them, and then one of them, the x and the y values switch. Let's look at one specific point, right? What's a really easy one you can find on this one? Yeah, this one is 0, 1, and then here it is 1, 0. Good. What's the other one? Yeah, Lily?
It's reflected over the y equals x line.
Yes, so part of the definition is that they are reflections over the line y equals x, which, did you guys see that line right here? That's how you can tell from the graph if they're reflected over that line. And then you can also tell if their x and y values switch. I said show algebraically that these two functions are inverses. So think back to when we were solving. What do we always do first? whenever you're finding an inverse, first step, switch your x and y. Now we have to solve. So I am going to solve for y, which means I have to get rid of that base. And how can I do that? How can I get rid of my base of a? Log base of a. Sorry. Because log base a and a are going to. All right, let's try it with the other one. Okay, so now I have to undo the log. And the inverse of a log function is an exponential function. Do you guys know what's going to cancel out with log base a? If this is your exponent and a is your base, right? Then wouldn't these two cancel out? So whatever we do to one side, we have to do to the other. Do you guys remember what this is called? It's called exponentiating. So you would exponentiate each side, which just means each side becomes the what? The exponent. Okay, so then a and log base a cancel out. You have a to the x equals y. So yep, we could prove algebraically that they were inverses. So I said, what is the crucial step when finding an inverse equation using algebra? What did we do first?
Change x.
Yes, we're going to switch the x and y variables or values. Okay, or your inputs and your outputs. So based on that, I said, what do you think happens to the domain and the range of inverse functions? Based on the fact that, Jonathan, what is the domain? How would we define the domain? Just in general, for any function. The domain is the set of possible x values. The range is the set of possible y values. So if the domain goes with the x and the range goes with the y's, but the inverses switch the x and y's, what happens? Yeah, the domain and range are going to switch in inverse functions. And then I said, think about how that's going to be implemented with the log function. So think about that as we're writing this down. So the domain and range switch for inverse functions. So last week we did exponential functions, which is the inverse of a log function. And wasn't there always something that was the same for all exponential functions? Which one was it? Yeah, the domain, right? The domain was always all real numbers, which means for the log, what's going to be all real numbers? Your range. Now those are going to flip. Okay, so the domain of the exponential function will be the range for the log function. Okay, and the same thing obviously is going to happen with the range too. Okay, so the domain of the exponential function is going to be the range of the log function. The range of the matching exponential function is going to be the range. So remember, there's lots of types of exponential equations. So they do have to be the inverse of each other, so your same base. So for example 3, we're going to graph the function, state the domain, the range, and the asymptote. And we're going to see how those are affected based on our new graph. So I have the negative log of base 10 of x. Now this says negative log base 10 of x, but what is special about base 10? You guys know what base 10 is in the log world? Yeah, it's called the common log, which means even if you didn't see a base on the log, it would be 10. Okay, so a lot of times you won't even see that. This would be the same thing as negative log of x. Now, before when we were making our tables, what did I put for our x values? What did we decide? We're going to be good x values for exponential functions. We did -2, -1, 0, 1, 2. Okay, now keep that in mind. Remember, x and y values are going to switch, which means instead of us wanting those to be our x values, we actually want them to be our y values. Okay, now in our properties, we said that the log of something always is something. Let's look back. The log of what? The log of 1 is always equal to 0. So that would definitely be something good to put on our chart. And then because this is negative for the 0, it's not going to make much of a difference. But now start to think of values that you can put on your chart that you won't even need a calculator for because you want them to cancel out. So log base 10 is going to cancel out with what? 10, right? Because log base 10 and 10 would undo each other. What would you be left with?
-1.
Yeah, good. Okay, so this would be 1. You apply the negative, -1. What's something else that would cancel out with 10 besides 10? What is it? No, but there will be something that has to do with that. She said -10. Let's actually look at that. So if you do the log of -10, what happens? Get a domain error, right? So the thing with logs is you can't take the log of a negative. We're going to explore that more, but it's based on your exponential function. Remember we talked about last week how the reason why your range is not all real numbers is because they get really, really small. They never dip into the negatives. That's why you can't take your log. You also can't take the log of 0. If you try to take the log of 0, not going to happen. But think about what is going to get you, in this case, -2. What's going to get you -2? Nope. Because that's 10 plus 10, 100, right? Because that would be 10 squared. Okay, so back onto your -10, right? It wouldn't be -10, but it could be 1/10 and 1/100th. And then wouldn't that get me 1 and 2 here? Yeah, so let's come up with a little bit of an easier way to think of this. Remember before we did 0, 1, 2, -1, -2? Now you can just think of it as the exponent. So isn't 10 to the 0, 1? 10 to the first is 10. 10 to the second is 100. So instead of just plugging in those numbers, you're plugging them in but as exponents. Okay, so whatever your base is, that's what you'd use for your base. So we aren't going to have our graph go up to 100, but we can have it go up to 10. So I'm going to make this out to 10 and -10, but my y's I am going to keep by 1, so 5 and -5. So if you remember, it's kind of like the opposite of what we were doing before. And then we're going to look and see where our asymptote is after we graph this. So I'm going to start at 1 at 0, because that one's pretty simple to graph. And then at 10, I'm at -1. And then for these, I have very, very small values of x that are going to produce 1 and 2. Because what is most likely happening here? It's getting closer and closer to what? Getting closer and closer to what equals 0? X, right? So isn't this getting closer and closer to the value that x is going to equal 0? Which means, what kind of asymptote do I have here? I have vertical. So just like my domain and range flipped, my asymptote flipped on me too. So this is going to be x equals 0. That is your vertical asymptote. Will there ever be? What?
Function that has a slant asymptote.
For your log, no. You'll just have your vertical asymptote. Now, for the domain and the range, you already saw there were restrictions to the domain. It can't be all real numbers because you saw I couldn't take a log of a negative or 0, right? Well, remember, your domain is all possible x values. You can use your graph to look at it. 0 to infinity. Look, can't you see that all of the points are to the right of this line? So that would be 0 to infinity. That's your domain. Your range, I can see this is going up to infinity. This is slowly going to be going down to infinity. So like we predicted earlier, your range is all real numbers. Okay, so let's try B. B is 1 plus the natural log of negative x. When you have that negative in the inside, do you guys remember what the transformation is? Yep, the reflection over the y-axis. Okay, so again, we're going to make a table. Now, because it doesn't have a base like this, what is the base here? Your base is E. We can go ahead and we can plug in values for that. So you can plug in your I started with well, let's think about it. So can I plug in 0? No, because we just saw that we can't take the log of 0, right? If you plug in 1 as x, wouldn't this be negative 1? Can we take the log of negative numbers? No. So really, what's the first thing I'm going to plug in? I'm going to try negative 1, right? Because then when I plug in negative 1, it really becomes positive 1. So then I'm going to take the natural log of positive 1, but what should it be? Should be 0, right? Because the log of 1 is 0, right? No matter what kind of log it is. And if you go under the log, you have your natural log. So this would be 1, again, because when we plug it in, and then 0 plus 1 is going to be 1. So then the next number I would plug in is negative 2, right? Which would really just be 2. And then I'm going to add 1 myself. So 1.7. If I plug in 3, again, remember this is negative 3. We're doing the opposite. So this would be 2.1. If I plug in 4, adding 1, I'd have 2.4. Okay, and then let's go ahead and plot these. I usually do just stick with 5 points. And I can do from 5 to 5 here, so that's fine with the points I have in my chart. Alright, so at negative 1, I'm at 1. At negative 2, I'm at 1.7. At negative 3, I'm at 2.1. At negative 4, I'm at 2.4. Negative 5, I'm at 2.6. Okay, so this curve. Now it might be helpful for me to see what happens in between those two. What's going to be in between those? What's in between 0 and -1? Yeah. Okay, so if I do 0.5, add 1, I'm at 0.3, so that might just help you. At -1/2, I'm at 0.3. Where's my asymptote going to be here? It's still at x equals 0. Remember when we did this with our exponential functions, it was tied to this number, right? So I guess that doesn't happen for this, right? Because it's not 1, it's still going to be x equals 0. Do you guys know what it's tied to? Say it again. Yeah, it's tied to what's inside the parentheses. Okay, so if I just have negative x here, if you want to find out what your vertical asymptote is, you can take whatever's inside the parentheses, set it equal to 0, and solve. Well, if you have negative x equals 0, then x equals 0. That's going to be your vertical asymptote. Okay, so to find your vertical asymptote, you can always take whatever is inside the parentheses, set it equal to 0. We still have to do our domain and our range. Well, our range, yep, down to infinity, slowly up to positive infinity. Our domain, all of our values are on the left side, which means my lowest x value is what? Negative infinity, and it'll go right up to 0. Won't include it because that's where your vertical asymptote is. All right, and then for part C, we have y equals log base 3 of x minus 1. So based on this, should we find our vertical asymptote right away here? Yeah, I just have to take x minus 1, set it equal to 0. And what's my vertical asymptote? X equals 1. Okay, and then I can even put that in if I want. I think I did put it in here. Okay, now this is a log with a base of 3. So really we want powers of 3 in here, except if it's x minus 1, what does that mean is happening to the graph? Yep, you're shifting it left or right. You're shifting it to the right by 1. So think about what value you'd want to plug in to get 3. What would you plug in to get 3? You'd plug in, when you plug in 4, isn't 4 minus 1 going to give you 3? And what's log base 3 of 3? Log base 3 of 3 would be 1. So if I plug in 4, I'd have log base 3 of 3, which would cancel out and make 1. All right, so one way you can think about this is 3 to the first power, but then you're just adding 1. Again, you're adding 1 because what way did we say we were moving? To the right. Okay, so to find our next one, you could think of it as, oh, what's 3 squared? 3 squared is 9, so 9 plus 1 would be 10. Right? Because if you have log base 3 of 9, that's 3 squared, which if those cancel out, you would get 2. So see how the exponent is going to be your answer here? It's just you have to make sure that you go with your transformations. So 3 to the 0 plus 1 is what? What's 3 to the 0? 1. 1 plus 1 is 2. My exponent is 0. This should be 0. If I did 3 to the negative 1, what's 3 to the negative 1? 1 over 3, right? 1/3. So isn't this just 1 and 1/3? And then I get negative 1. 3 to the negative 2 is 1 and 1/9. And I get negative 2, so then I can plot my points from there. All right, so if I have 10, That's not going to fit on my graph, so I'm going to go 4, 1. So 1, 2, 3, 4, up 1. Okay, and then I have 2, 0, so 1, 2. I have 1 and 1/3, negative 1, 1 and 1/9, negative 9. So this is getting closer and closer in this direction. Okay, going right down my asymptote there. So what's my domain going to be? So look at your points, right? They start at what value? 1, and they go to infinity. So 1 to infinity, your range, all real numbers. All right, and then we were just going to talk about the vertical asymptotes. Okay, so I said, why are the asymptotes vertical? What do vertical asymptotes represent? Yeah, what?
Can I just answer the question of why?
Okay, sure.
It's because like exponential functions and horizontal asymptotes, it's the whatever the word is of
The inverse.
yes, the inverse of exponential function.
But think about why they are in terms of the domain. So vertical asymptotes can't be crossed, right? Because think about your domain when we were doing rational functions. What was always excluded from the domain? Your vertical asymptotes, because that's where, yeah, that's where it can't be part of your domain, right? So think about logs. What can't we take the log of? We can't take the log of 0. We can't take the log of negative numbers. So these asymptotes are occurring where there are gaps in our domain. Okay, so the asymptotes are vertical because they represent where the domain is undefined, and since you can't take the log of 0, they are going to represent the values that make whatever's inside 0. Asymptotes, I'm going to just say vertical asymptotes represent where the domain is undefined, which for logs is at 0. The vertical asymptotes occur where the log would be 0, which is why we set it equal to that. Okay, so the reason why it's x equals 1 is because if you were to plug in 1, you get the log of 0, and that can't happen. Right? The rest of them are going to follow from that. That's why we don't have anything in this section here. I said, when is the vertical asymptote not equal to 0? Yeah, John?
When there's a shift to the x.
Okay, good. So you can say when there's a horizontal shift. Okay, and then if you're looking at it in terms of your equation, you'd have to have a value added to the x inside the log. So I said when a number is added, subtracted to x inside the log. Okay, and then I said, what is the vertical asymptote for y equals log base 3 of x plus 1? X would equal negative 1. And that's because x plus 1 would equal 0. So then x would equal negative 1. last thing is a story problem. As we continue on in our log function, we will be dealing with lots of story problems and radioactive materials. So you can determine the age of an artifact by measuring the amount of radioactive carbon-14 remaining in it. If D sub 0 is the original amount of the carbon-14 and D is the amount remaining, then the artifact's age in years is given by this equation. Okay, what we have to do is find the age of an object if the amount remaining is 73% of D sub 0. Okay, so 73% of D sub 0 is 73% of the original amount. So then we can interpret that as 0.73 D sub 0. Okay, and that would be your amount remaining. So that would be your D. Okay, so if your amount remaining is 73% of the original, to find it, you would just do 0.73 times D sub 0. And then we can go ahead and plug this in for D. And our age of the object is A. So we're going to do negative 8,267 times the natural log of, so if D is equal to 0.73 D sub 0, I can pull that in. And then what happens inside my parentheses?
The D sub 0 cancels out.
Yeah, so then all I have to calculate is the natural log of 0.73. Okay, and then remember we're finding this amount in years. So when I do my natural log, 0.73 multiplied by, I do have a negative 8267. This is approximately, we're just going to round, 2,602 years. Okay. All right, and then here is your homework.